Another thing that this second derivative can tell us is we can actually use the second derivative to identify relative extrema in some cases as well. So if we let f be a function such that f prime of c is equal to 0 and the second derivative of f exists on an open interval containing c, if f double prime at c is greater than 0, then f has a relative minimum at the point cf of c, and if f double prime of c is less than 0, then f has a relative maximum at cf of c. Now this only works if you actually get a positive or negative value. If f double prime of c equals 0, then the test fails. Now if the test fails, it doesn't mean that f doesn't have a relative maximum or minimum. It could be that it actually is, or it could be neither. But if the test fails, you have to use the first derivative test on the intervals surrounding that point. Now here's why it works. You're still looking at critical numbers, so these are still places where f prime of c equals 0 or doesn't exist, or actually it has to be in this case where it's equal to 0. But if you're looking at a concave upward graph like this, you can see that it does have a low point or a dip. It's got a valley. So if it's upward, it's going to have a minimum, and if it's downward, then it's going to have that high point or a maximum. So that's why this works. So let's look at an example. I want to find the relative extrema of negative 3x to the fifth plus 5x cubed. So I'm going to start by setting f prime of x equal to 0. So f prime of x is negative 15x to the fourth plus 15x squared. And if I set that equal to 0, if I factor out a negative 15x squared, I get x squared minus 1. So I get x equals 0 and x equals plus or minus 1. Okay, so those are my critical values, or my critical points. And I also need f double prime of x in order to actually do the second derivative test. So f double prime of x, we're going to take this derivative, we're going to have negative 60x cubed plus 30x. So my second derivative test, notice I'm not going to have any intervals here. I'm just going to plug in my critical points, which are negative 1, 0, and 1. I'm going to plug them directly into f prime of x. So this one would be negative 60 times negative 1 cubed plus 30 times negative 1, which actually gives me 30, so that's greater than 0. Here I would get negative 60 times 0 plus 30 times 0, so this one gives me 0. And for this one I would end up getting negative 30, which is less than 0. So my conclusion for this one, because f double prime of x is greater than 0, I am concave upward, so that means that I have a relative minimum. Now be careful with that. A positive f double prime means I have a relative minimum, so it's the opposite of what you may expect, but it is because of the concavity that's happening there. At 0, the test fails. Okay, and here I get I have concave downward, so I have a relative maximum. Now I do want to find f at both of those values because I need to know the y value. So f of negative 1 would be negative 3 times negative 1 to the fifth plus 5 times negative 1 cubed, which is negative 2. And f of 1 would be negative 3 times 1 to the fifth plus 5 times 1 cubed, which is 2. So I have a relative min, I know for sure, at negative 1, negative 2. To deal with this one where the test fails, we do want to set up the intervals on either side. Now you don't have to look at all of the intervals when the test fails for a point. You just need to look at the interval around it. So I would look at negative 1 to 0 and 0 to 1 because we're basically going to be using the first derivative test when the test fails. So I would pick my test points at maybe negative 1/2 and 1/2. I would plug those back into f prime of x, and if I plug a negative 1/2 in to that negative 15x to the fourth plus 15x squared, I get a positive number if I plug in a positive 1/2 I also get a positive number. So this is increasing, increasing. And so we can say that x equals 0 is neither. So my conclusion is that I have a relative minimum at the point -1, and we found that to be -2, and I have a relative maximum at the point 1, 2. So that would be my answer here. So we're going to do another one of these. I'm going to start by finding f prime of x, which would be 3x squared minus 6x, and I'm going to set that equal to 0. So I'd factor out the 3x and have x minus 2. So I get x equals 0 and x equals 2. Those are my critical values, or my critical numbers. I'm going to find the second derivative, which is going to be 6x minus 6. And so to do my second derivative test, I'm going to plug in my critical numbers, of which there are 2 of them, 0 and 2. I'm going to plug those into f double prime of x. So that'll be 6 times 0 minus 6, or -6, which is less than 0, and 6 times 2 minus 6, or 6, which is greater than 0. So my conclusion here, this is less than 0, it's concave downward, so that makes that a relative max. This one is concave upward because it's positive, so that makes that a relative min. And I do need to find f at each of those, so f of 0 would be 0 cubed minus 3 times 0 squared plus 3, which is 3. So we have a relative max at 0, 3. And f of 2 would be 2 cubed minus 3 times 2 squared plus 3, which is -1. So I would have a relative min at 2, -1. So that is my answer. And in this case, the second derivative test worked for the whole function. So that is the second derivative test. Now I do want to caution you because I know that these problems are starting to sound very similar. So if you're asked to find the absolute extrema on a closed interval from A to B, you can figure out how to do that from section 3.1. If you're asked to find the relative extrema, all relative extrema, then you can either do that with the first derivative test, which is in 3.3, or in some cases you can use the second derivative test, which we just talked about in this section. Okay, and if you're asked to find points of inflection, or concavity, that is in 3.4. That's where you use the second derivative. So make sure that you're clear about which type of problem is which, and let me know if you have any questions about that and if you need that clarified.